So, let us next look at continuous cooling transformation diagrams, otherwise known as CCT diagrams. We had already noted that TTT diagrams are drawn for isothermal holding conditions. That means, these are representative of transformation times under isothermal hold treatment. And we are also noted that under practical circumstances, we have heat treatments. That means, we follow certain things known as time temperature cycles or time temperature procedures, in which typically there are steps involving cooling the sample. That means that there are treatments of course, where you might isothermally hold, but there may be steps within the time temperature cycle, within the heat treatment cycle, wherein you may actually cool the sample. The cooling rate may or may not be constant, means the cooling rate itself could change during the process. The rate of cooling may be slow, like for instance, we may leave a sample inside the furnace and allow the sample to cool along with the furnace, which takes a long time. In other words, the cooling rate will be small, or we may take the sample and put it into water, which we call quenching in water, in which case my cooling rate obtained is high. Sometimes of course, we will see in coming examples that we may actually take a melt and cool it at even much higher rates than that allowed by quenching in water. So, in practical terms, TTT diagrams have the limitation, and we have to draw a separate set of diagrams called the continuous cooling transformation diagrams or CCT diagrams, wherein transformation times, and of course, whenever we are talking about transformation times, we include the products obtained and the microstructure which we overlay on these diagrams are noted using constant cooling treatments and not constant temperature treatments. A diagram drawn for a given cooling rate, for instance, I use a dT by dt, which is approximately constant, is typically used for a range of temperatures or a range of cooling rates, thus avoiding the need for a separate diagram for each cooling rate. That means, though I may have a TTT diagram which is only valid for a certain range of cooling rates, I may, or strictly speaking for just one cooling rate which is held constant, I may use it for a range of cooling rates around that cooling rate. And often you would note that TTT diagrams are also used for cooling rate experiments, but in such circumstances we have to keep in view the assumptions involved and the approximations which underlie the drawing of those TTT diagrams. CCT diagram for eutectoid steel is we will talk about next, and we will overlay on the CCT diagram also the pre-existing TTT diagram, so that we know the two for comparison. The important difference for the eutectoid steel is the difference that for the CCT, that means under cooling treatments, bainite cannot be formed. So, this is how the CCT diagram looks, and the curves which correspond to the TTT diagram or the original TTT diagram are drawn in green color. So, these are my original TTT curves which are here. So, this is my original TTT curves which are both these ones, this for the start and this one for the finish, and the current CCT curves are the ones drawn in blue. So, this is my start line, and as you would note that two products have been marked in this diagram, the Martensite which is obtained at high cooling rates and the Pearlite, but there is no Bainite. So, again like before, my starting point is of course my austenite, and I am cooling my austenite using a constant cooling rate, like, and this constant cooling rate dT by dt as shown on the right hand side here could be which is represented as T dot. That means, this d temperature by d time is represented T dot, and we can use cooling rates which is increasing. For instance, in this case there are two cooling curves shown, one with T1 dot which is greater than a slower cooling rate which is T2 dot. Both these T1 dot and T2 dot are constant cooling rate curves. A few important points we will note before we describe this diagram in detail. We have to note that this x axis as before is in a log scale. Bainite cannot form by continuous cooling. Constant rate cooling curves look like curves, I mean they are not straight lines, but they are curves in this plot because of this log scale used along the x axis. And an higher cooling rate curve typically has a higher slope, and this slope is negative of course, as compared to a slower cooling rate. That means, T1 dot is a faster cooling rate as compared to T2 dot, and this straight line, and if you had plotted normal temperature versus normal time, we would have obtained a straight line, but because the x axis is a log scale, we see that these curves start to look, they are not straight, but they are curved. And as before, no treatment curve can be drawn where the time decreases or remains constant. We know that time always has to flow in the positive direction. Therefore, we should not draw any curves. For instance, I am not allowed to draw a curve on this which goes, say for instance, like this here. Furthermore, I am not even allowed to draw curves like these on this, for instance, because in such a case my starting point is in the Pearlitic phase field, and for drawing all TTT diagrams for eutectoid steel, we have noted that we are interested in the eutectoid transformation. That means that my starting phase has to be the gamma phase, which is my austenite, and I study the transformation of this gamma into various alphas plus Fe3C or the Martensite, which are the two possible microconstituents or phases or the microstructures obtained after this transformation. So, when I cool my sample, say using a slow cooling rate like T2 dot, then I obtain that I start with, of course, my at above 723 degrees as my austenite. Then on cooling, I obtain a final product which is pearlite. Once the curve, of course, has crossed a curve like this here and here, I have started with pearlite start, and this means pearlite start, and this would be my pearlite finish, and that means whole of my gamma has got transformed into pearlite, and therefore, these intersections here right here have no meaning. So, this we should not read into these intersections. At this point, all the starting product has transformed into pearlite, which is a microconstituent, and therefore, no further transformation of this pearlite can take place. On the other hand, suppose I look at a curve like T1 dot, in which case the cooling rate is faster. I see that I start again with this point, which is the above the eutectoid temperature, say the point P. I hit my start curve for formation of pearlite, but I do not cross the finish curve. The finish curve for pearlite is here, this line, and I do not cross this line, but I only hit the start line. That means I land up with a microstructure which is pearlite, and the remaining austenite can transform into martensite. Therefore, I have a combination of phases now. And of course, I can avoid the nose of the CCT diagram and therefore go to higher cooling rates, in which case I will obtain a fully martensitic phase right here. So, I can use a cooling rate, which we will see in the next coming slides. So, to summarize this slide, here I have my TTT diagrams, CCT diagrams, which have been overlaid on the TTT diagrams. The green curves are my original TTT diagrams, the blue curves are my new CCT diagrams. If I use constant cooling treatments, even though I am using a constant rate of cooling T dot like T1 dot or T2 dot, which is nothing but T dt by dt, d capital T by d small t, these curves, these straight lines start to look like curves, because now time is in log scale. Then furthermore, I have noted that if you completely transform all the gamma into, say for instance pearlite, then further intersections of this curve with, for instance, the Martensite start or the Martensite finish lines have no significance. And the most important thing to reiterate, there is no Bainite formation possible by constant cooling. When you look at these curves, you notice that the blue curve is shifted with respect to the green curve. So, we can ask this question, why is the CCT curves to the right of the corresponding TTT curves? That means, why does it take longer time, for instance, to form? Suppose I am here, why does it take longer for, I am at say at this temperature here, why does it take longer time to form pearlite when I compare these two curves? So, this is my first one intersection, say A is for TTT and B is for TTT. Why does it take longer time for me to produce pearlite when I use a constant cooling rate rather than a constant temperature? Now, the answer for that is that as a cooled sample has spent more time at higher temperature before it intersects the TTT curve, which has been virtually superimposed. That means, now actually I have to talk about, since I am using cooling rate, I have to actually talk about intersection with the CCT curve and not the TTT curve. The transformation time is longer at higher temperatures. We know this from the curves, that if I go to higher and higher temperatures before the nose, then I note that it takes longer and longer time for me to the transformation to take place. And since the sample, though is intersecting actually the curves in this region, but it has spent more time at a higher temperature where the transformation times are longer. This is above the nose, of course. This means CCT curve should be the right to be has to be to the right of the TTT diagrams, and that is how it has been drawn. So, now we have introduced a new tool, which is now my CCT diagrams, which has important practical applications, as we shall see now. and therefore, I can use these CCT diagrams in what we might call heat treatment cycles or heat treatment applications, wherein we want to say for instance start with eutectoid steel and produce microstructures with various hardness or various strength. Now, the common cooling treatments and typically the labels used or the names used for these are full annealing, normalizing, oil quench and water quench, and these have been arranged in the increasing order of the cooling rate. For instance, water quench has the highest cooling rate, next is lower is oil quench, normalizing is even lower and annealing treatment is even lower. And the typical microstructures produced for these cases are when you do full annealing, like for instance by using a furnace cooling treatment, you get coarse pearlite. If you use a normalizing treatment, which is for instance what we call air cooling, that means you take the sample out of the furnace and leave it in open air and you do not do any further thing to it, you obtain typically a fine pearlite. If you quench it in oil, we can produce a mixture of martensite and pearlite, and if you quench it in water, we can produce pure martensite. And we will draw the corresponding cooling curves for all these in the coming slides on the CCT diagrams. To produce full martensite, we have noted that we have to avoid the nose of the TTT diagram, or to more precise, I can now, since that we have introduced the CCT diagram, so I can call this the CCT diagram. So, we have the CCT diagram and I have to avoid the nose of the CCT diagram, and that means that I have to, my quenching rate has to be fast enough for that. Once I avoid the nose of the CCT diagram, then I can produce a sample in which all the sample is transformed into martensite. But of course, we have to keep in mind that in all practical situations there might be some amount of retained austenite, that means all the martensite might not have transformed into all the austenite might not have transformed into martensite, and we may have some residual amount of austenite which is called retained austenite. Now, here in naming these treatments like water quench, oil quench, normalizing, etc., and also noting the quench rate, we have made some simplifications, and there are further parameters which we need to take into account to actually determine how the quench rate changes within a particular treatment, which we will take up in one of the coming slides. So, let us overlay now the different cooling treatments on top of the CCT curve. So, for instance, the highest cooling rate is for the water quench here, in which case I avoid the nose of my TTT diagram and I produce a full martensitic structure, and to reiterate, some amount of retained austenite might be present in practical situations. If you use a slightly higher cooling rate, slightly lower cooling rate, which is produced by given by an oil quench, that means I take my sample out and put it inside an oil. Typically, there are special oils for this purpose, which will give you a high cooling rate, but not as high as water quench. Then I can produce a microstructure which is a combination of martensite and pearlite, because now you started your pearlitic transformation, but this pearlitic transformation was not completed and the remaining. So, this is where my pearlite started, but then it was not completed, you never hit this curve which is the pearlite finish curve. Therefore, what happens is that the remaining austenite transforms into martensite when you hit the martensite start curve, and therefore, you have a microstructure which consists of martensite plus pearlite. Now, suppose you have a even lower cooling rate, as I mentioned, by leaving a sample outside the furnace, then you can produce a fine pearlitic structure, or if I use an even lower cooling rate which is called annealing treatment or a full annealing treatment, in which case I leave my sample inside the furnace, allow the furnace to slowly cool, then I can obtain a coarse pearlitic structure. And as I again pointed out, this coarse pearlitic structure, of course, we will note the properties very soon, but we have to note again that in the case of normalizing and full annealing, these intersections have no meaning. So, these intersections should not be given any importance. Now, the important thing, of course, is that the whole heat treatment which we are studying here is that for a single composition, and now we are talking about eutectoid steel or a 0.8% carbon steel, I can produce different microstructures, and of course, we have seen certain microconstituents being part of it like pearlite, and these different microstructures can give rise to a varied set of properties. That means, what I am doing here should be technically called microstructure engineering, and I am using microstructure engineering. So, let me write this in bold, because one of the important ways of defining materials engineering is that materials engineers give a lot of importance to microstructure engineering, and this is true not only for mechanical properties, but also for certain magnetic and many other properties. So, what we are doing is microstructure engineering. So, I have here a handle on the properties by doing not changing the composition. That means I have eutectoid steel, but I vary my heat treatment, which means I vary my temperature time cycle, so as to get a varied set of properties, and these varied set of properties are obtained because for each one of these heat treatments I produce a different microstructure. So, I have a handle on the properties not via the composition, but via the microstructure, which is controlled by heat treatments. And of course, here we are considering some simple uniform heat treatments, but in real life we may use a combination of heat treatments, and further I may use what is might call thermomechanical treatments, in which case not only I am using temperature cycles, but also I am giving mechanical deformation, in which case I have further control over the final properties I obtain, the microstructure, etc. So, here we have seen that in this that I can use different cooling treatments starting from austenite, my starting phase gamma, the gamma phase field, and by giving different cooling treatments I can get different microstructures, which can be a full martensite, martensite plus pearlite, fine pearlite or coarse pearlite, and I can get different properties, which we will see in the coming slides. Now, we have to note that what are the typical cooling rates of various processes. Now, we have said that, for instance, typically noted that water quench has a higher cooling rate as compared to oil quenching, which is a higher rate compared to air cooling, and furnace cooling we said that was the slowest cooling rate. So, what are the typical cooling rate, and here of course, we are noting it in terms of Kelvin per second or degree Celsius per second, because these both are equivalent. So, I could also use a different unit here, which is degree Celsius per second. So, on the low end of course, is my furnace cooling, in which case I obtain a cooling rate which is order of 10 power minus 5 to 10 power minus 3 Kelvin per second. Air cooling can give you 1 to 10 degrees per second cooling rate, that means the sample would fall at the fastest rate about 10 degrees Celsius per second. And now of course, we have to note, and we will pay more attention to it in the coming slides, that what we are talking about the cooling rate is the surface cooling rate, because the quenching medium or the medium is not in direct touch with the interior of the material, and therefore, what we can the medium has access to is only the surface, and therefore, suppose I had a sample, for instance a cylindrical sample, what I am talking about is the cooling rate on the surface. So, suppose this is my sample, I am monitoring the cooling rate on the surface here. So, this is my surface cooling rate, and not at the bulk or the interior, where the cooling rate could be different, which is determined, which is sort of controlled by the conductivity. Oil quenching can give you an higher cooling rate of the order of about 100 degrees Celsius per second, water quenching even higher, about 500 degrees Celsius per second, and these two stars indicate that there are further details involved, which we will come in the consider in the coming slides. There are further techniques like splat quenching, and I will go to the board to explain you what is splat quenching. In splat quenching, we typically have a substrate of high thermal conductivity. For instance, you may have a copper substrate, and you can put a molten pool of material, say for instance a molten, you could melt using induction some metal, and you can purge it with argon, and this molten pool of jet could fall on this stream and get flattened out. So, this is so when this molten metal falls on the substrate of copper, for instance, which has a high thermal conductivity, then very high thermal cooling rates are experienced by especially the initial surface which is falling on the substrate. And since the amount of metal being put here is very small, typically most of the metal feels a very high cooling rate. So, this is my splat quenching technique, and there are variations which are called gun quenching, wherein the velocity of the jet can be very high, the molten pool can be very high, and I can obtain cooling rates of the order of about 10 power 5 Kelvin per second. Of course, measurement of this cooling rate, that how do you obtain such a high cooling rate itself is a challenging task, and typically some microstructural features could be used for that. Now, even higher cooling rate is obtained by process known as melt spinning, and the different, and you can obtain cooling rates of the order of about 10 power 6 Kelvin per second. And in melt spinning, typically, like unlike the splat cooling, what we use here again is a disc, a rotating copper disc, and this rotating copper disc, for instance, and this rotation speed could be of the order of about 3000 rpm, 3000 revolutions per minute, and your molten stream of metal would fall on this. And since the wheel is rotating, no single point would see a lot of metal falling on it, and therefore, and for instance, you would form a foil which comes out of it. So, you will get a thin sheet which comes out of it, and this sheet, of course, most of it would have felt a very high cooling rate of the order of about 10 power 6 Kelvin per second. So, this process is known as melt spinning. And this process gives you ribbons. So, this is my rotating copper wheel on which I throw a jet of stream of metal, and I can get very high cooling rates. Now, and if the cooling rate is very, very high, in fact, you may not even obtain a, for certain compositions, you will not even obtain a crystalline product, you may obtain an amorphous product. Further, even higher cooling rates have been reported for processes like evaporation, sputtering, which of the order of is about 10 power 9 Kelvin per second. And of course, we should note that even at such high cooling rates, for instance, suppose I take a metal like aluminum, it is difficult to amorphize aluminum even using such high cooling rates. So, with me I have many processes with which I can use a different kind of a cooling rate, increasing cooling rate as you can see downward, and therefore, I can have a handle on the microstructure which is produced. Two things, of course, not only that I can control the micro constituents like pearlite, but I can control the fineness of the pearlite. That means, if you talk about here, suppose I am talking about fine pearlite here, that means my pearlite would consist of alpha and Fe3C, which are finely distributed like this. So, this is my fine pearlite. On the other hand, in the case of coarse pearlite, I may obtain the wavelength of this coarse pearlite might be larger. So, this is my coarse pearlite and this is my fine pearlite, and as you would expect that the fine structure has a higher hardness as compared to the coarse structure. So, I have a handle on the cooling rates, and as we shall see later, within oil quench and water quench, further we may control the parameters to get a range of cooling rates. So, we have already seen this microstructure. So, let us talk a little bit more about how do we obtain this pearlite and martensite, and also bainite, and what are the growth process involved or what are the issues involved in their phase transformation. So, we already seen that this pearlite consists of alternating lamella of alpha and Fe3C, and this is for now for a eutectoid composition. This phase forms by nucleation and growth process, and we will see that very soon, and typically it occurs by heterogeneous nucleation at grain boundaries, and the interlamellar spacing is a function of the temperature of transformation, or as we have seen, because this is in the case of the TTT diagram. Suppose I am talking about a TTT kind of scenario, and suppose I am talking about a CCT scenario, then I have to talk about the cooling rate. In other words, we already seen a faster cooling rate gives you a finer microstructure, and of course, similarly if you do the transformation at a higher temperature, then you obtain a finer pearlite, because there you might remember that we actually did this some time back, that when we drew the TTT diagrams, we had noted that at higher temperature we obtain the coarse pearlite, and at lower temperature where the nucleation rate is expected to be higher, but the growth rate lower, we obtain a fine pearlite. Now, we also noted that the finer spacing structure has a higher hardness. Of course, we are talking about the eutectoid transformation, which is gamma giving alpha plus Fe3C. Now, what is the mechanism by which this lamellar structure arises in pearlite? So, let us talk about heterogeneous nucleation at a gamma 1 gamma 2 interface. So, gamma 1 is one grain of gamma, gamma 2 is another grain of gamma, and we are talking about heterogeneous nucleation of one of the phases, for instance pearlite, at a grain boundary of austenite. Let this precipitate be bound by a coherent interface on one side and an incoherent interface on the other side. Coherent interface is one where the planes are continuous across from one phase to the other, and incoherent interface where there is no continuity of planes from one side to the other. So, this I can draw schematically here. Suppose I am talking about phase 1 and I am talking about phase 2, I can talk about planes being continuous across these. Of course, there might be distortion because the lattice parameters may not be same, but atomic planes are continuous. If I talk about so this is my coherent interface. In an incoherent interface, the atomic planes have no matching from one side to the other. For instance, this could be one set of atomic planes, the other set of atomic planes could be like this, and there is no matching of planes from one side to the other. Now, an interface being coherent or semi-coherent has important consequences in terms of the strain energy involved. It also has important the chemical energy involved, and a coherent interface has a lower chemical energy, but a higher strain energy. And also the important point to note is that, for instance, suppose I am having a semi-coherent interface on this side and an incoherent interface on the other side for this gamma, the Fe3C gamma interface, I would notice that the incoherent interface is more mobile or glissile as compared to the coherent interface. And therefore, since the semi-coherent interface or the incoherent interface is more mobile or glissile as compared to the coherent interface or a semi-coherent interface, then this side would grow as compared to the opposite side. So, therefore, I would have now the growth of not this one, the growth of the alpha Fe3C in this direction. So, this growth direction will be more. Now, if Fe3C grows, then what happens is that the region surrounding this Fe3C precipitate will be depleted in carbon, and the condition would be right for the nucleation of alpha adjacent to it. So, now after this Fe3C has gone some distance, an alpha could actually nucleate next to it and actually grow. So, an alpha can nucleate and grow. This orientation relationship, that means this alpha and Fe3C have some kind of fixed orientation relationship, crystallographic orientation, and this is typically referred to by the name of Kurjumov-Sachs relationship. And the Kurjumov-Sachs relationship is defined as the 100 plane in cementite is parallel to the 111 type of or 11 plane in gamma. The 010 of cementite is parallel to 110 of gamma. The 001 of cementite is parallel to 1/2 of gamma. And we already noted cementite is an orthorhombic structure, and we are noting the orientation relationship. Though at this stage this is a little advanced topic for most beginners, but we have just noted that there is an orientation relationship between the alpha and Fe3C. Now, of course, next to the this Fe3C plate, on the other side again you could have a nucleation of alpha and growth of alpha. So, these two are alpha, and this is now my Fe3C, and slowly I can have this process repeated again and again, and I have what you might call a colony of pearlite growing. So, this is now my colony of pearlite. And so, I am a pearlitic colony. Further, some of this Fe3C may actually branch and giving rise to richer microstructures due to this branching process. So, let us summarize the mechanism by which such a lamellar microstructure, the pearlitic lamellar microstructure which you see here in this micrograph, for instance, you have this alternating lamella, and between two lamellae of alpha there is a lamella of Fe3C. How do we get such a lamellar microstructure? Is that first we can assume that the heterogeneous nucleation is a dominant process. Say for instance, Fe3C first forms at an interface between gamma 1 and gamma 2, 2 grains of gamma. After this nucleation, we would note that typically there are coherent and semi-coherent or coherent and semi-coherent and incoherent interfaces. The incoherent interfaces are glissile or mobile, and they grow, and after certain growth of certain amount of Fe3C, you would notice that alpha nucleates in adjacent regions like here, and these alpha continue to grow, and this process is repeated by adjacent nucleation of various alpha and Fe3C lamellae, that you get a pearlitic colony. And we also noted that the alpha and Fe3C are not randomly oriented, but there is a fixed orientation relationship typically given by the Kurjumov-Sachs relationship, which has been listed here below. That means there is a crystallographic orientation between my alpha and Fe3C. So, we have a brief idea of how the pearlitic transformation takes place by heterogeneous nucleation at the gamma 1, gamma 2 boundaries, and especially the role of the what you might call the coherency of the interface in such a growth process. We had noted also another micro constituent which is Bainite, and this Bainite we have previously noted consists of alpha and Fe3C. Now, in case of Bainite, the way this alpha and Fe3C is distributed is different, and for instance, this is one picture of a Bainite, and there are more pictures of Bainite in the next slide here. For instance, this shows you some rich microstructure of Bainite here, and this is 0.8% carbon sample which was quenched in a salt bath given at 400 degrees Celsius and then held for 2 hours. So, we note that we have to hold isothermally to produce Bainite, and that means continuous cooling cannot give us Bainite. And this is another micrograph on the right hand side where you see at an even higher magnification the Bainitic structure. So, this is slightly different from the Pearlitic structure, and even on the right hand side that you can see that there is a Bainitic structure wherein you have these sheets of Bainite which is shown in an AFM image. So, this structure does not have this alternating lamella like in Pearlite, and typically these structures are finer because now the transformation is at a lower temperature where nucleation is the more dominant process, and therefore, you expect to obtain a fine structure of Bainite, and this Bainite has a higher hardness as compared to Pearlite, as we shall see soon. The Bainite which is formed at higher temperatures, say around 350 degrees Celsius isothermal hold, has a feathery appearance and often called a feathery Bainite. Bainite formed at lower temperature 275 degrees Celsius has a needle like appearance, and what we mean by needle like or acicular appearance is that the structure actually consists of some needle like regions. So, this is my, and the feathery appearance is meant that it actually has a very diffuse like feather like outline instead of having sharp outline. So, that is how the feathery Bainite looks, and such a Bainite with needle like shape is called a acicular Bainite. So, this is my acicular Bainite here. The process of Bainite formation again involves nucleation and growth, because this is not a shear deformation shear involving process like Martensitic transformation, but involves nucleation and growth. This acicular Bainite formation involves surface distortions, and we will note later that such kind of surface distortions are also observed in Martensitic transformations. Now, another additional complication comes because at lower temperatures the carbide may not be the usual Fe3C, but could be the orthorhombic Fe3C, but could be an epsilon carbide which is an external structure and which is more carbon in it compared to the cementite. So, we could suppose I do this transformation and I do not, of course, I have to avoid the nose of the TTT diagram. So, I have my TTT diagram here for transformation alpha to Fe3C. Of course, my usual axis would be temperature and time, and suppose instead of doing at a reasonably low temperature, I go to even lower temperatures and do my transformation, I may sometime obtain a carbide known as the epsilon carbide, which has an external structure and which has even more carbon in it. So, we considered here some aspects regarding Bainitic transformation, and we will come to the properties of such a Bainite produced in one of the coming slides. So, once again let us have a closer look at the microstructure here, where we see that the Bainite does not look lamellar as like the case, and you can even see the outline of these, some of these sheets are very different as compared to the Pearlite. Now, let us try to understand some more details about the Martensitic transformation. Martensitic transformation we shall of course consider now for eutectoid steel, and one of the important things we said about the Martensitic transformation was that it is produced by a diffusion less process, number 1. Number 2, we said it involves shear. Number 3, we said it produces a very hard product in the case of the iron eutectoid steel, and we had also noted that it is hard but brittle phase, and therefore, I would like to see that how this Martensitic transformation takes place in steel, what are the issues involved crystallographically, and what are the issues involved with respect to the sample itself and the sample deformation. So, let us start with a few characteristics of the Martensitic transformation. First of all, that the shape of the Martensite form is lenticular, or they consist of thin parallel plates, and for instance, this could be one of the Martensitic plates which has been shown here as labeled as alpha prime. So, this is kind of a lens kind of a plate which forms. So, if you look at a grain of austenite within which such a martensite for instance would form, then you may notice that suppose this is my grain of austenite within my martensite form, this martensite could form like a plate like this. The second thing of course is that this process is associated with shear or shape change and does not involve long range diffusion. And this shape change can clearly be seen in the form of surface distortions as shown in this schematic here, that if this plate actually intersects the surface, this shear leads to a distortion of the surface as clearly seen in this schematic drawn here. There is one characteristic which is that there is one plane which is called the strain is imposed in such a way, the shear strain, such that there is an invariant plane. There is one plane which remains invariant during this entire transformation. For instance, suppose this is my basal gamma in which I am forming my alpha prime, which is my martensitic phase, then I would notice that there is one plane which remains undistorted. So, this is called the invariant plane, and therefore, the strain which is involved in this martensite formation has to be consistent with the fact that there is one invariant plane in the whole transformation. And this interface plane between martensite and parent place remains, this invariant plane remains undistorted and unrotated during the whole transformation. This whole process therefore has to involve 3 steps. Step 1 and step 2 we will concentrate in the current set of slides, that it involves what is called the crystallographic Bain distortion or the Bain deformation, wherein there is an expansion or contraction of the lattice along certain crystallographic directions leading to homogeneous dilation. So, the Bain distortion itself leads to a certain dilatational process. Of course, the dilatation depends on the x or y direction, as we shall see in the coming slides. Now, to keep an invariant plane, certain secondary shear distortion is involved, and this for instance has to be accommodated by either slip or twinning. Further, there is a need for a rigid body rotation, which we shall not talk about in the coming slides. So, let us summarize this slide before we see how this Bain distortion takes place, how the secondary shear distortion takes place, or why is that need for the secondary shear distortion to keep the invariant plane, all these things. In this slide we are talking about a formation of a martensite which has got a lenticular morphology, and this lenticular morphology gives rise to deformations, especially if the plate intersects the surface as shown in the schematic below. Now, this invariant plane strain which is observed experimentally has to be understood in terms of 3 steps, which is the Bain distortion, the secondary shear distortion and a rigid body rotation. So, in the martensitic structure we have the gamma FCC which forms a body centered tetragonal structure, the alpha prime structure, and the composition during this whole process, and we produce martensite typically by quenching. Therefore, as we talked about, we taken water and quench our sample from the austenite region, we can produce martensite, and the composition does not change. That means there is no long range diffusion involved, like in the case of formation of pearlite or bainite from the gamma. So, this martensite involves change in crystal structure. That means, you go from gamma FCC to alpha prime, which is BCT. Now, we have started here with 0.8% carbon steel. First, let us understand that suppose we had pure iron, we do not have an 0.8% carbon steel. What happens to this iron when we quench it from the gamma phase field or the gamma region? So, the iron FCC has this kind of a lattice as shown here, and for this we can choose an alternate unit cell as shown in the blue color. Please note that there is no phase transformation involved so far. What we are talking about is the choice of an alternate unit cell as marked in blue color. Now, this is an body centered tetragonal cell which can also as I will describe this FCC structure. Only thing, normally we do not choose this unit cell as a preferred unit cell because of the fact that the cell has a lower symmetry as compared to the lattice. Now, if I cause phase transformation of this by quenching, and I know at room temperature as iron as a BCC structure. So, the end product has to be a BCC structure if I start with an FCC structure, and now I am assuming, as you know, there is no carbon involved in the process. This phase transformation involves contraction of the C axis, that means the C axis contracts, while the axis which is drawn here, the new A axis, which is now my new A axis for the body centered tetragonal cell, expands about 12%, and so therefore, there is an contraction along the C axis, expansion along the A axis, such that the final product is one in which all my 3 lattice parameters along the A prime, which is here for the new unit cell, and this is of course originally a C axis, which is now also becomes A prime after the phase transformations. That means that by this kind of a contraction, by this kind of a deformation, I can understand how the BCC unit cell forms from the FCC structure, and there is no volume change involved, and the resultant structure BCC, the C by A ratio of this structure is 1, because now we have 2 lattice parameters A prime which is constant, and the C which is now becomes the new A prime after 20% contraction is the same as the lattice parameter along the basal directions. Therefore, if I take pure iron and quench it from the from high temperature, I have this FCC to BCC phase transformation, and the final product is as expected BCC. Now, the product BCC is not very hard, because now we are talking about pure iron, and we will see later in the next slide that suppose I do not start with pure iron, but I start with an iron carbon alloy in the gamma phase field and quench it for, and now we will consider eutectoid composition, then I will obtain a hard product. So, we will see how this hard product, which is Martensite, is obtained. In other words, if I have carbon, I do not land up with BCC, but I land up with the body centered tetragonal, and we will try to understand how this body centered tetragonal structure comes about. In the presence of carbon, and we know that this carbon is present in the octahedral voids of the cubic closed packed crystal, or the FCC crystal as commonly known as, the contraction along the C axis is impeded by the carbon atoms. So, where are these carbon atoms present in the FCC? And of course, now I have my original unit cell like here before, the FCC unit cell with these 3 as my reference axes. Additionally, I have my blue unit cell, which is now my body centered tetragonal unit cell, and further in the same diagram I have marked the positions where the carbon atoms could be potentially present. And you can notice that these carbon atoms are present, some of them along the C direction like this one, these ones are present along the C direction, but there is no carbon atom present along the new A prime direction. So, there is no carbon atom along the A prime directions of the body centered tetragonal cell. But of course, since we are talking about a dilute solution of carbon in iron, that implies not all the octahedral voids are occupied, because in an FCC structure or a cubic closed packed structure, the number of octahedral voids is the same as the number of the atoms in the unit cell, but therefore, only a very small fraction of the octahedral voids are occupied. But what we have drawn here are all the potential sites where carbon atom can sit. And now, when my Bain distortion takes place, or the distortion which we saw previously at 20% contraction along the C axis and 12% along the A axis, this kind of contraction tries to take place when I quench from higher temperature. You can notice that the 2 A axis, as I am marking here, these A axis are free to expand, because there are no carbon atoms in their path. On the other hand, the C axis is partially impeded by presence of carbon atoms, the contraction which was 20% before, and the end product is such that so for instance, you see a carbon atom is sitting here, this would obstruct my contraction along the C direction, and therefore, instead of obtaining a final product which is BCC, I land up with a final product which is BCT structure. So, this is now not my BCC, but a body centered tetragonal structure, in which case the C axis is slightly larger than the A axis, and the C to A ratio is of the order of 1:1.1. So, this is a slightly distorted body centered cubic structure, which is a body centered tetragonal structure, wherein carbon atoms are sitting along the C direction like here, which have as again only a part of those potential sites are actually occupied by carbon, and this impediment gives rise to a body centered tetragonal structure. Now, the overall volume change involved is of the order of 4.3%, and such a large volume change implies that there is a lot of strains involved in this Martensitic transformation, and these strains if not relieved later on by heat treatments can actually cause this material to be brittle, and this can lead to cracking of the material. And needless to say, this volume change depends on the amount of carbon present in the starting Gaustenite. So, we can now formally define what is known as the Bain distortion. Homogeneous dilation of the lattice, which is expansion or contraction along crystallographic axis leading to the formation of a new lattice, is called the Bain distortion, and this involves minimum atomic moments, because we already noted that long range diffusion is not part of the Martensitic transformation. So, we are now ready to summarize and of course, let us start with see some typical Martensitic microstructures. Again you can see that in Martensite again we have these kind of acicular structures, but this is a typical Martensitic microstructure you would obtain, and needless to say such a product is actually brittle and would need further heat treatments to make it an industrially important material. So, there are other microstructures of Martensite which is not that clear, but this structure of Martensite seems reasonably clear when you see that there is all these Martensitic sheets which are present. So, let us summarize our details about Martensitic transformation. So, Martensitic transformation involves shear, and typically certain lenses of Martensite form by, and the shear process could lead to surface distortions. And to understand this Martensitic transformation, I need to understand Bain distortion, that means crystallographic distortions, and secondary shear, which is accommodated by slip or twinning. And the first part, which the Bain distortion we have understood so far, in which case we have noted that presence of carbon leads to the stops the contraction along the C axis, and therefore leads to a body centered tetragonal structure in the end, and not a body centered cubic structure. And this process overall involves lot of strains, about 4.3% volume change, and this strain is accommodated within the microstructure, and therefore such a material, unless this residual strain is relieved somehow, can lead to a lot of cracking in the material. Now, let us try to understand why do we need this shear to accommodate this invariant plane strain condition. So, let us assume that there is an plane here, and this of course, these are schematics to understand this. There is a plane, for instance, the one drawn in Len, a crystallographic plane, and typically this is an irrational plane, and this is also called the irrational habit plane. And this irrational habit plane has to remain undistorted during this whole process of Martensitic transformation. Now, step 1 of course, is what we saw is some kind of a dilation or contraction, and let us consider dilation of this lattice. So, during this dilation you notice that this plane which was originally present here has gone to the new position, which is now marked in red. So, this is my new position of the plane. That means that now my plane, which was expected to remain exactly in the original place undistorted, has got distorted. In fact, it has got stretched, because the original length was A prime, and now the new position is A B prime, and the A B prime is longer than A prime. Now, to accommodate the fact that you do experimentally observe an invariant plane strain condition, we can actually understand it by imposing what we call secondary shear, and the secondary shear can cause shear of this structure, so, but bring the plane originally plane black to the A prime condition. Of course, this leaves the plane A prime undistorted, therefore, I get my invariant plane strain condition, but the problem is here that suppose I shear my crystal as such, then the crystallography of the in other words, I land up with a lower symmetry crystal, but this is not observed, and therefore, what we see how is this shear accommodated is by two processes typically. One is by slip or twinning. So, for instance, in the left hand side there is a schematic which says that even though I have a shear on an average I can have an undistorted crystal structure. That means the unit cell of the crystal does not get distorted, but I can have and this is therefore two mechanisms by which this secondary shear is accommodated. One is slip, another is twinning. In slip, of course, I can see that the unit cell remains the same, and now I have a shear being accommodated. That means the average shape remains undistorted. So, I can have it that, or in the right hand side, of course, you can see that these crystallographic planes are twinning, and this twin can actually accommodate my shear. Please note that, of course, this is not my new unit cell. What we have drawn here are these kind of planes which are being reflected, and therefore, this is shown the reflection of these planes. That means, now this is my twin planes. So, these are my twin planes. So, this twinning leads to twinning can be used to actually accommodate my secondary shear, but we have to note that we do need secondary shear to understand the invariant plane shear, plane strain, and this shear can be accommodated either by slip or by twinning. So, let us summarize the characteristics of the Martensitic transformation. The Martensitic transformation obviously occurs without a change in composition. That means, if I start with eutectoid steel, I land up with eutectoid steel, and the process occurs by shear deformation with no need for long range diffusion. Atomic moments required only are a fraction of the interatomic spacing, as we have seen that this Bain distortion does not involve, or the secondary shear does not involve large scale atomic movements. The shear changes the shape of the transforming region, results in considerable amount of shear energy, and also is responsible for the plate like shape of martensite, the lenticular shape. The amount of martensite formed is a function of the temperature to which the sample is quenched, and not a function of the time to which you hold the sample. The hardness of martensite is further a function of the carbon content, but with increasing carbon content, though the hardness increases, but also the sample becomes more and more brittle, and we will have to undertake treatments like tempering to actually get some amount of ductility back. In other words, I can do a quench treatment which gives martensite, and so this quenching has to be followed by tempering treatment, so that I have a combination of ductility and strength. In other words, the toughness of my sample can be enhanced.